Welcome to another explainer. I am absolutely thrilled you're here today because, well, we're looking at one of the most incredible, lightning-fast mechanical processes in the human body. We're going to treat this screen like a giant interactive whiteboard. We'll explicitly visualize, label, and map out the exact biological machinery operating inside your head right this very second. We are demystifying eye accommodation.
So get this, did you know your eye can focus on objects both near and far, faster than literally any high-end camera lens on the market? It's wild. It's a staggering fact. Now, mastering this topic is absolutely crucial if you're aiming to ace your O-level biology exams, but honestly, it goes way beyond that. This isn't just about passing a test, it's about truly appreciating the dynamic, high-speed mechanics of our own anatomy. Here is our quick roadmap for this explainer. First, what is accommodation? Second, focusing on distant objects. Third, focusing on nearby objects. Fourth, common exam mistakes. And finally, number 5, a quick review and takeaways.
Okay, let's dive right into this. Section 1. What is accommodation?
Put simply, accommodation is the process where the eye changes the shape of its lens to focus on objects at various distances. To really picture this, let's compare a macro view of a physical camera lens to the micro view of its biological equivalent. On the left here, we're looking at a macro view of a camera with its mechanical focus ring turning. You can see the glass elements physically moving back and forth along a track to focus the light. But on the right, your eye does something arguably much more elegant. Instead of sliding a transparent lens back and forth, your eye physically morphs the actual shape and curvature of the lens itself.
All right, Section 2, focusing on distant objects.
Let's break this down step by step in a chronological flowchart so you can track the exact physical forces at play. Step 1. Your ciliary muscles relax. Notice those outward directional arrows popping up to show this relaxation. Step 2. Because those muscles relax, the suspensory ligaments, which are basically these string-like structures holding the lens, tighten. See how the tension lines on the diagram are turning bold? They're pulling taut. Step 3. This mechanical tension pulls on the edges of your elastic lens, causing it to flatten out. And finally, Step 4. Because the lens flattens, the focal length increases. Notice that dimension line extending horizontally right from the lens to the back of the eye? That perfectly visualizes the increased focal length.
And this brilliantly illustrates the mathematical physics of that flattened shape. When an object is far away, the light rays reaching your eye are essentially parallel. You can see those straight horizontal vector arrows coming in from the left side. Because the lens is flatter now, it bends or refracts this light less severely. That increased focal length dimension we just talked about perfectly matches the distance to the retina at the back of your eye. So the flatter lens ensures those parallel vector lines converge precisely at a single pinpoint spot on the retina. That's what gives you a crystal clear image of that distant mountain or far-off building.
Let's move to Section 3 and see how this builds, focusing on nearby objects. We are completely reversing the mechanics now. This flowchart highlights the inverse relationship. Step 1, your ciliary muscles contract. Notice the bright red inward arrows showing that muscular contraction. Step 2, this contraction actually releases the outward pull on the suspensory ligaments. Take a look at the visual tension lines. They're now loose and wavy, which means they've relaxed. Step 3, well, because there's no more tension pulling its edges, the natural elasticity of the lens causes it to spring back and thicken up, becoming highly convex. And Step 4, this thick, bulbous shape immediately decreases the focal length. Watch the dimension indicator for the focal length shrinking dynamically on screen.
Now, let's observe the physics of this thicker lens. When an object is close to you, the light rays bouncing off it are diverging, or spreading apart, by the time they hit your eye. You can see those spreading vector lines coming in from the left. To capture those diverging rays and force them to a point, your eye needs a much stronger refractive power. That thick, highly convex lens acts like a powerful magnifying glass. It forcefully bends those diverging light rays inward. The sharply decreased focal length ensures that even though the light was spreading out, it is aggressively converged to land precisely on the retina once again.
Moving on to Section 4, common exam mistakes. There is a massive, stark contrast here between myth and reality. Under myth, on the left side, we've got a big red X over a graphic of an entire eyeball squishing and elongating, and another red X over arrows showing a lens sliding forward and backward on a track. This is completely false. Your eye doesn't squash like a stress ball, and the lens doesn't slide back and forth like a camera barrel. On the right side, under reality, we have a green check mark next to an isolated view of the lens. The reality is that the change is purely 100% localized to the curvature of the lens itself. The overall shape of your eyeball remains completely rigid and perfectly intact during this whole process.
So, what does this all mean? Let's wrap up with Section 5, quick review and takeaways.
This table perfectly maps the inverse relationships we've just discussed. It's basically a cheat sheet. Reading across the top row, if the object distance is distant, the ciliary muscles relax, the ligaments tighten, the lens flattens, and the focal length increases. Now reading across the bottom row, if the object distance is near, literally everything flips. The ciliary muscles contract, ligaments relax, the lens thickens, and the focal length decreases. If you can visually memorize the opposing flow of these two rows, you will absolutely dominate any question on this topic. It's a perfect logical seesaw of biological mechanics.
So here are your final actionable takeaways. Number 1, remember that accommodation is purely about changing the lens shape, nothing else. Number 2, master that inverse relationship we just looked at. When the muscles relax, ligaments tighten, and vice versa. And number 3, honestly my biggest tip for exam prep. Don't just read the text. Practice drawing these dynamic diagrams yourself. Sketch the lens, draw the tension lines of the ligaments, add directional arrows for the ciliary muscles. Translating these concepts into your own visual flowcharts is absolutely the best way to lock them into your memory. Visual aids are almost always required in exam questions for a reason.
I want to leave you with this final thought. Look at your computer or phone screen right now. Got it? Okay, now look at the farthest wall in your room, or out a window. Done? In that split second, your ciliary muscles just relaxed, your suspensory ligaments pulled taut, your lens flattened out, and your focal length increased to catch those parallel light rays. Next time you shift your gaze, try to imagine that incredible, invisible, lightning-fast biological machinery operating right inside your own head. Can you feel your ciliary muscles working? It's pretty amazing to think about. Thank you so much for joining me for this explainer. Keep observing the amazing science inside you, and I'll catch you in the next one.